Tonight we're going to dismantle an image of the end of everything. An image that has been sitting quietly in the back of your mind since you were a child staring at a page in a science textbook, or listening to a teacher describe a candle burning down to nothing. You know the picture. You may not remember when you first saw it, but it's there. A universe that begins with a flash expands outward, and then at the end of all things either collapses back into a single point, a mirror of its own birth, or slowly fades to black like a fire running out of wood. Neat, symmetrical, comforting in a strange way. A story with a beginning, a middle, and a clean final page. And that picture is wrong, not slightly wrong, not off by a decimal point. Wrong in the way a child's drawing of a house is wrong, recognizable, but missing every window, every room, every hallway, every hidden staircase inside. The real ending of the universe is larger, stranger, and quieter than almost anyone has ever told you. And here is the question we're going to circle for the next 2 hours. A question so strange, so patient, that it might keep you thinking long after this video is over. What if the universe does not end at all? What if, instead, it simply forgets how? Before we go any further, if you find this kind of slow, deep exploration into the nature of reality fascinating, a quiet like or a subscribe genuinely helps this channel keep making these long-form journeys through the cosmos. It's a small thing on your end, and it means an enormous amount on ours. Now, let's begin. Because in the next 2 hours, we are going to walk somewhere very few people ever walk. We are going to start with the ending you were taught, and we are going to watch it break in front of us. We are going to meet the invisible force that shattered it, a force that makes up nearly 70% of everything that exists, that no one has ever seen, that no one has ever touched, and that, until only the last year or two, we thought we understood. We were wrong about that too. And in the last year, using the largest three-dimensional map of the cosmos ever made, a map built from millions of galaxies stretching back 11 billion years, we've started to see the first cracks in that force. Hints, whispers, statistical shadows suggesting that the thing we thought was pushing the universe apart forever may be slowly, quietly weakening. And if that is true, then every ending you have ever been told is on the table again. Every single one. We are going to walk through those endings, one by one, tonight. We are going to look at the slow, cold death, the one where the stars simply run out. We are going to look at the violent one, the one where space itself is torn apart, atom by atom, in a screaming crescendo. We are going to look at the mirror ending, where the universe collapses back into a single, unimaginable point. We are going to look at the endless one, the bounce, where the end is only the middle of a longer story. And we are going to look at the most terrifying one of all, an ending so quiet, so instantaneous, that if it began right now on the other side of the galaxy, you would never know it was coming. It would already be here. But even those 5 endings are not the strangest part of what waits. Because when we follow the front-running scenario, the slow one, the freeze, all the way down its long road, we will find something that no textbook diagram has ever captured. We will find eras. Not years, not billions of years, eras, each one lasting so much longer than the last that the previous era becomes a single, forgotten instant. Stars end, then galaxies end, then matter itself ends. And then in the deepest, longest era of all, only black holes remain, and even they, one by one, in flashes separated by unimaginable silences, will vanish too. And that is when the question changes underneath us. Because at the very bottom of that long, dark hallway, at the end of the end of the end, we run into something we did not expect. We run into the possibility that ending itself is a word invented by beings who die. A word borrowed from human lives. A word the universe never learned. That is where we are going tonight. So before we take the first step, let me ask you something. And I want you to actually think about it, not just scroll past. When you were young, the very first time you were told that the universe had a beginning, did anyone ever tell you that it also had an ending? Or did you just quietly assume, in the way children do, that it would go on forever? I'd love to know what your mind did with that thought. Tell me down in the comments what you were taught or what you weren't. And now, take a slow breath. Because before we can understand how the universe will actually end, we have to return one more time to the ending you were promised. The tidy one, the clean one, the one that lived in the back of your mind for years without you ever quite examining it. We have to understand it in detail before we can watch it break. So let's go back to the classroom. Let's go back to that first diagram. And let's begin gently with the ending you were taught. There is a diagram somewhere in your memory that looks something like this. A small dot on the left side of the page. From that dot, an expanding cone stretches outward toward the right, like the mouth of a trumpet opening slowly across time. Inside the cone, tiny illustrations, a swirl of gas, a first star, a spiral galaxy, a solar system, a blue and green planet, and then at the far end, either the cone closes back down to a point, or it fades gently into gray. That is the universe you were taught, a beginning that is almost nothing, a middle where everything happens, and an ending that is either a mirror or a sigh. It is a picture so tidy, so satisfying to the human mind that it slipped into our imagination without resistance. It felt correct. It felt earned. It felt like the shape a universe ought to have. And for most of the 20th century, that was the entire debate. Not whether the universe would end, that was assumed, but which of two clean, beautiful shapes it would end in. The first shape was called the Big Crunch. It was a mirror image of the beginning. The idea went like this. Gravity is always pulling. Every galaxy, every star, every atom in the universe tugs on every other. And if there is enough matter in the cosmos, if the total pull of all that gravity is strong enough, then the expansion set off by the Big Bang will one day slow down, stop, and reverse. The galaxies, currently drifting apart, will begin to drift back together. The distances between them will shrink. The background sky will grow warmer instead of colder. Stars will crowd into each other. And in the final act, everything that has ever existed will collapse back into a single, unimaginably hot, unimaginably dense point. a mirror of the original singularity from which it all began. A beginning and an ending that are, in a sense, the same event seen from opposite ends of time. That was the first ending. The second was gentler. It was called the Big Freeze, or sometimes the heat death. In this version, gravity is not strong enough to reverse the expansion. There is not enough matter in the universe to pull it all back, so the galaxies keep drifting apart forever. The universe keeps expanding slowly, quietly, at a steady pace, and over long stretches of time, everything cools. Stars burn through their fuel. New stars form less often, and then, eventually, not at all. Galaxies drift so far from each other that no light from one can ever reach another. And the cosmos, once a blazing, crowded thing, becomes a vast, cold, silent field of dying embers. That was the second ending. Two shapes. One that snaps shut like a book. One that thins out like breath in cold air. For decades, cosmologists went back and forth between them, trying to decide which one was ours. And the choice, in the end, seemed to come down to a single number, a number they called omega. Omega was simply the ratio between the actual density of matter in the universe and the exact density that would bring the expansion to a perfect, eternal halt, neither collapsing nor drifting apart. If omega was greater than 1, there was enough matter, and gravity would win. Big crunch. If omega was less than 1, there was not enough, and expansion would win. Big freeze. And if, by some cosmic coincidence, omega was exactly 1, the universe would coast forever at the delicate boundary between the two, a knife's edge balance, expanding forever but always just barely slowing. 3 tidy possibilities, 3 clean stories. Pick a card, any card. The universe would tell us which one it had drawn. And to understand why cosmologists even trusted this framework, we have to go back a little further. We have to go back to a man on a mountain in California in the 1920s, quietly measuring the light of distant galaxies through the largest telescope in the world. His name was Edwin Hubble. Hubble did not set out to shatter the cosmos. He was a careful, patient astronomer. And what he was doing night after night was measuring the color of the light coming from faint smudges of light in the sky. Smudges that we now know are entire galaxies, but which at the time were the subject of a raging debate. Were they small clouds inside our own Milky Way, or were they enormous, distant island universes of their own? Hubble found that they were island universes, and then he found something stranger. When he measured the light coming from them, he noticed that almost all of them were stretched, reddened. Their light was slightly longer in wavelength than it should have been, and the further away they were, the more stretched their light appeared to be. This effect is called redshift, and it has a simple, staggering explanation. The galaxies were not sitting still. They were moving away from us. And not just some of them, almost all of them, in every direction we looked, as if the entire universe were quietly running away from itself. That was the moment the universe stopped being a static, eternal thing in the human mind. That was the moment it became a story. A story with motion, a story with a plot. Because if everything is moving apart today, then yesterday it was closer together. And the day before, closer still. And if you rewind the film all the way back everything must have started at the same place at the same instant. A single, unimaginable event from which all of space and time unrolled. The Big Bang. Hubble's redshift was the fossil footprint of that event. Every galaxy in the sky was a runner, still fleeing outward from the starting line of an explosion that happened nearly 14 billion years ago. And once you accepted that the universe had a beginning, a question that had never really been asked before became suddenly, urgently obvious. What is going to happen to it? For the next 70 years, that is the question cosmology chased. Astronomers weighed the universe. They tried to measure omega. They counted galaxies. They mapped the motion of clusters. They studied the microwave afterglow of the Big Bang itself. A faint bath of radiation left over from the moment the young universe cooled enough for light to travel freely. And by the mid-1990s, they had a pretty firm expectation. Gravity was slowing the expansion. It had to be. There was simply nothing else in the equations that could push a universe apart. Gravity pulls. That is what gravity does. So the expansion had to be decelerating. The only question was it decelerating fast enough to eventually stop and reverse, big crunch, or too slowly, so that expansion would win forever, big freeze? Two teams of astronomers on opposite sides of the world set out to answer that question with a beautiful and elegant idea. They would look for a specific kind of exploding star called a type Ia supernova. These supernovae have a wonderful property. They are more or less always the same brightness. When a certain kind of dead star, a white dwarf, reaches a very specific mass, it detonates in a very specific way, releasing a very specific amount of light. Every single time. If you can find one and measure how bright it appears from Earth, you can work out exactly how far away it is. And if you can also measure its redshift, you can work out how fast the universe was expanding when that light left it. Do this for enough supernovae at enough different distances, and you can chart the expansion of the universe across billions of years. You can measure directly how much it has slowed down. Two teams, one led by Saul Perlmutter in Berkeley, the other by Brian Schmidt and Adam Rees in Australia and the United States, went to work. They chased their supernovae for years. They collected them one by one. They plotted them carefully on a graph. And then in 1998, both teams, working entirely independently, looked at their data, and they saw the same impossible thing. The universe was not slowing down. The universe was speeding up. Take a moment with that. Because that is the moment the tidy diagram in your memory silently died, years probably, before you even learned to draw it. The distant supernovae were dimmer than they should have been. They were dimmer than any decelerating universe could produce. They were dimmer, in fact, than a universe expanding at a steady pace could produce. The only way to make sense of them was to accept that space itself had been stretching faster and faster over the last several billion years, not just expanding, accelerating. As if something, everywhere, at every point in the universe, were quietly pushing outward and had been getting stronger and stronger the more the universe grew. Nothing in physics allowed for that. Nothing. And yet there it was, written in the light of dying stars from across the cosmos. The two teams checked their work, they rechecked it, they tore it apart, they looked for dust, they looked for calibration errors, they looked for any way at all to make the answer be the old, tidy answer. There wasn't one. In 2011, all three of the leading astronomers behind the discovery, Perlmutter, Schmidt, and Rees, were awarded the Nobel Prize in Physics for it. And the tidy diagram broke. Because think about what this meant. If the universe is accelerating, then omega, the number cosmologists had spent 70 years trying to measure, was not the whole story. There was something else in the equations, something that did not pull, something that pushed, something so vast, so pervasive, that it was quietly overpowering the combined gravitational tug of every star and every galaxy in the observable universe. Something invisible, something that did not fit into any theory we had, something that 27 years later we still do not really understand. We gave it a name because that is what humans do when they cannot yet give a thing an explanation. We called it dark energy. Not because it is dark in any poetic sense, but because it is dark in the sense that we cannot see it, cannot detect it, cannot isolate it. We know it is there only because of what it does to the cosmos. It makes the galaxies rush apart faster and faster, and it will keep doing that, we think, for as long as it exists. And here is what almost no one tells you about that discovery in 1998. Almost overnight, both of the endings you were taught became obsolete. The big crunch could not happen because the universe was not slowing down, it was speeding up. There was no reversal coming. Gravity had already lost. And the gentle big freeze, the slow, cold fade was no longer really gentle. It was going to be much colder, much emptier, and much lonelier than anyone had imagined. Because if the expansion is accelerating, then galaxies do not just drift apart. They are pushed apart more and more violently, until eventually the space between them stretches faster than the light between them can cross. And when that happens, they simply vanish from each other's sky. The tidy ending you had in your head was not just incomplete. It had already been erased 3 decades ago by a handful of dying stars in another galaxy, whose light had traveled across the void of space for billions of years just to arrive at a telescope on Earth and tell us the truth. And here is the thing about that truth. It raised more questions than it answered, because it forced us to admit that we did not know what most of the universe is made of. It forced us to admit that whatever is driving the expansion, this dark energy, is doing something that our best theories cannot explain, using amounts that our best equations get wrong by a factor of 10 followed by 120 zeros. It forced us to admit that the future of everything hinges on a thing we cannot see and do not understand. And it left us with a single question that has haunted cosmology ever since. A question that, in only the last year or two, has finally started to shift, thanks to the largest map of the universe ever made, and a set of results so surprising that some of the researchers involved will not yet say out loud what they suspect. What is this thing? What is dark energy really? And is it really as constant, as steady, as unchanging as we have assumed? Because if it isn't, if it is changing, evolving, weakening, growing, then everything we just said about the ending of the universe changes with it. Every scenario is back on the table. Every future is possible again. So before we go any further tonight, I want to ask you something. And I want you to sit with it for a moment, honestly, before you answer. When you look up at the night sky, when you see those quiet, ancient points of light hanging above you, does it feel to you like the universe is holding still? Does it feel like everything is in its place, patient, eternal, unmoving? Or if you look long enough and you let yourself feel it, does it feel like something is slowly, quietly pulling away from you? Which sensation is stronger when you actually pay attention? Tell me in the comments. I want to know which one your body feels. And now, take another slow breath. Because to understand what really happens at the end of the universe, we have to understand the thing that is pulling it apart. We have to meet dark energy face to face. We have to look at what it is and what it isn't. We have to look at the strange, brand new measurements that are quietly rewriting our expectations of the far future. And we have to prepare ourselves gently for the possibility that everything we thought we knew about how this all ends is about to change again. So let's step into the dark. Imagine for a moment that you are floating in the deepest, quietest, emptiest patch of space you can find. Not near a star, not near a galaxy, just empty. A cubic meter of nothing hanging in the vast dark between the great cosmic structures. In every direction around you for millions of light years, there is essentially no matter at all. No hydrogen, no dust, no light, just an unimaginable stillness. And yet, in that cubic meter of nothing, in that emptiest place you can find, something is happening. Something is pushing. Gently, quietly, everywhere, all at once. The empty space itself is expanding, not into anything, not away from anywhere, just expanding, growing, stretching, as if space itself has a kind of pressure to it, a soft, insistent outward force woven into the very fabric of the vacuum. And that force, whatever it is stronger than gravity, stronger than the combined pull of every galaxy in the observable universe. It is winning, and it has been winning quietly for the last 5 billion years. That is dark energy. We do not know what it is. We have never seen a particle of it. We have never isolated it in a laboratory. We have never watched it interact with anything. We know it exists only because of what it does, because of the way it stretches the distances between galaxies faster and faster, year after year. It is, by the most conservative estimates, about 68 to 70% of everything that exists, not 68% of a small ingredient, 68% of the entire universe. Everything you have ever seen or touched or been, every atom in your body, every star in the sky, every grain of interstellar dust, all of it added together, is only around 5% of what is really out there. Another 27% roughly is dark matter, a different mystery for another night. And the rest, the overwhelming rest, is this invisible pressure. The thing we cannot see, the thing we cannot explain, the thing that will decide in the end how it all ends. Let that sink in for a moment. Almost 7/10 of everything is a force we have no theory for. A force we know is there only because we watched it push a distant supernova a little further away from us than it should have been. A force so strange that when physicists try to calculate its expected value using our best equations, using the same quantum field theory that predicts the behavior of every particle in your body, the answer they get is wrong. Not slightly wrong. Wrong by a factor of 10 followed by 120 zeros. That is not a small mismatch. That is the largest disagreement between theory and observation in the entire history of science. If you tried to write out that number in ordinary notation, you would run out of paper before you finished the zeros. Physicists have a name for this. They call it, sometimes with a kind of dark humor, the worst prediction in physics. And it is the reason why, when you talk to a cosmologist about dark energy, they tend to grow quiet for a moment. Because the honest truth is this: we built our understanding of the universe on physics that gets the biggest ingredient in that universe almost infinitely wrong. We named the thing, but we did not solve it. And yet, for almost 20 years, there was a comforting story about it. A story that let us sleep at night. That story went like this: perhaps dark energy is not something exotic. Perhaps it is not some new field or particle. Perhaps it is just a property of empty space itself. A tiny, unchanging amount of energy baked into every cubic centimeter of the vacuum, the same everywhere, the same forever. A constant, a background hum. A number woven into the equations that has been there since the beginning of time and will still be there at the end. This idea has a name. It is called the cosmological constant. And it has a strange history because Albert Einstein invented it more than 100 years ago, then abandoned it, and then, decades after his death, the universe insisted on giving it back. When Einstein wrote down his equations of general relativity in 1915, he noticed something troubling about them. His equations suggested that the universe could not sit still. It had to either be expanding or contracting. Nothing in his math allowed for a static, eternal cosmos. But at the time, everyone, including Einstein himself, believed the universe was static, eternal, fixed. So he added a small term to his equations by hand to keep the universe from moving. That term was the cosmological constant, a gentle mathematical fudge to hold the cosmos still. And then Hubble discovered that the universe was expanding. Einstein removed the term. He reportedly called it the greatest blunder of his career. And for nearly 7 decades, the cosmological constant sat in the dusty back rooms of physics, a relic of a mistake, until 1998, until those distant supernovae came back with their impossible answer. And suddenly, that old, discarded term fit the data almost perfectly. Add a small cosmological constant back into Einstein's equations, and the numbers worked. The acceleration of the universe was exactly what you would expect from a tiny, constant energy density of empty space. Einstein's greatest blunder was apparently correct after all. So we accepted the story. Dark energy was a cosmological constant. It was baked into the vacuum. It was, quite literally, the tension of nothingness, the same tension yesterday, today, and forever. And once we accepted that, the ending of the universe was more or less locked in. Because if dark energy never changes, then it will always push and always at the same strength. Gravity will lose. Expansion will keep accelerating. The galaxies will keep drifting apart faster and faster until they slip beyond each other's horizons and vanish. The universe will grow colder, emptier, and darker forever. A slow ending. A quiet one, but a certain one. We built our models on that certainty. We built our cosmology on it. We taught it in universities. We wrote it into textbooks. And in the 2 decades that followed, the cosmological constant became the invisible backbone of what we call the standard model of cosmology. The model we call, in shorthand, lambda CDM. Lambda for that little Greek letter that stands for the cosmological constant. CDM for cold dark matter. Together, those 2 ingredients, a constant dark energy and a slow-moving invisible matter, reproduced almost every observation we could make of the large-scale structure of the universe. Almost. There were always a few strange corners, a few numbers that did not quite add up. The rate at which the universe is expanding today, for example, seemed to have 2 different values depending on how you measured it. One from the cosmic microwave background, the ancient afterglow of the Big Bang, and another, slightly higher, from nearby stars and supernovae. That disagreement, called the Hubble tension, has been quietly nagging cosmologists for years. And there were other, smaller inconsistencies too, subtle mismatches between predictions and observations that no one could quite explain, but that everyone quietly assumed would go away with better data. Better data has, finally, arrived. In the deserts of Arizona, at a place called Kitt Peak, there is a telescope that has spent the last several years doing something that no telescope has ever done before. It has been building a 3-dimensional map of the universe on a scale that dwarfs every previous survey ever attempted. Its name is the Dark Energy Spectroscopic Instrument, or DESI, and it is the joint work of more than 900 researchers from over 70 institutions around the world. Every night, DESI points at the sky, and using a robotic array of 5,000 tiny optical fibers, each one moved by its own miniature positioner into precisely the right spot. It captures the light of thousands of galaxies and quasars at once. Then, from the redshifts of those objects, it locates each one in 3-dimensional space, not just its position on the sky, but its distance from us, its place in the great cosmic web. And what DESI has done over the last few years is chart the expansion of the universe going back 11 billion years, nearly the entire age of the cosmos, with more precision than we have ever had before. The first results came in 2024. The second, more comprehensive results came in 2025. And when the scientists put the DESI data together with observations of ancient supernovae, with the leftover glow of the Big Bang, and with the way distant light is bent by the gravity of galaxies along its path, a technique called weak gravitational lensing, something extraordinary began to appear, something they had not expected, something that shook them. The DESI data on its own is still consistent with the old story. A constant dark energy quietly pushing space apart, unchanged since the beginning of time. If you looked at DESI alone, you would say the cosmological constant is fine. Nothing to see here. But when you combine it with everything else, with the supernovae, with the cosmic microwave background, with the weak lensing measurements, with every other precise probe of dark energy we have, the picture starts to tilt. The combined data no longer matches a constant. It matches more closely a dark energy that is changing over time, a dark energy that was slightly stronger in the distant past, a dark energy that is slightly weaker now, a dark energy that appears, and this word matters, to be evolving, weakening, cooling in a sense, fading. Now we have to be careful here. These are hints, not proofs. The signal is not strong enough yet to overturn the standard model on its own. The researchers themselves are extremely cautious, and they should be. The universe has surprised us before with what looked like signals that later turned out to be measurement error. But the DESI team, in their own words, put it this way: guided by the principle that the simplest explanation is usually the best, a principle scientists call Occam's razor, the simplest explanation for what they are seeing has shifted. It used to be that the simplest fit to the data was a constant dark energy. It is not anymore. The simplest fit now is one where dark energy changes. And that is enormous, because if dark energy is changing, then everything we said about the ending of the universe, the slow, cold, certain fade, is not certain at all. Think about what this means gently for a moment. For 27 years, we have lived inside a story where dark energy is eternal and unchanging, where its outward push is a settled fact, where the future is fixed. The stars will fade. The galaxies will drift beyond each other's horizons. The universe will grow cold. That was the plot. But if dark energy is fading, then that plot is up in the air. Because a fading dark energy could mean many different things. It could mean that the acceleration of the universe is slowing. That in some far distant future, the outward push will weaken enough that gravity begins to matter again. That the great galaxies begin to slow their retreat, and maybe, eventually, begin to fall back toward one another. It could mean that the big crunch, the ending we had discarded, is quietly climbing back onto the list. Or in more extreme versions, a fading dark energy could still swing the other way, could weaken now but strengthen catastrophically later, tearing space itself apart in an ending we have not yet described tonight, but that has haunted cosmology for 2 decades. An ending called the Big Rip. We do not yet know. That is the honest truth. The universe has whispered something to us through the light of millions of galaxies collected by 1,000 pairs of hands and a robotic array in the Arizona desert. And we have not yet decoded what it said. But it has whispered enough that every ending we thought was off the table is back on it. There is another possibility too, which we should name honestly. The signal might turn out to be a mirage. Some cosmologists, very careful, very respected cosmologists, think the apparent evolution of dark energy could be an artifact. It could be an illusion produced by the way we model the enormous voids and dense walls of the cosmic web. When the universe is not perfectly smooth, and it isn't, not up close, the average expansion we measure can look, from the inside, like an evolving dark energy without actually being one. That is one hypothesis. It is not confirmed. But it is a reminder that we are not yet at the end of this story. We are at the beginning of a new one. And that, I think, is one of the most quietly astonishing things about the moment we are living in. For most of human history, the ending of the universe was a matter of philosophy, or of theology, or of guessing. In the last 100 years, it became a matter of measurement. And in the last 24 months, the measurement has started to move. Right now, tonight, as you are listening to this, there are cosmologists in laboratories on 4 continents pulling all-nighters over the DESI data. There are teams designing the next generation of surveys, the Euclid Space Telescope, the Vera Rubin Observatory, and others, that will collect the light of tens of millions more galaxies over the next decade. There are physicists arguing gently and passionately in journal papers and at conferences over what the shifting signal means. The story of how the universe ends is being rewritten in slow motion in our lifetime, and you were born just in time to watch it change. So before we go further, sit with that for a moment and tell me honestly, if scientists announced tomorrow that dark energy is fading, that the great outward rush of the cosmos is slowing down quietly, and that in the deep future the universe may not drift apart forever, but instead may pull itself back together, how would that feel to you? Would it feel like good news? A universe that gathers itself back in, rather than one that scatters into nothing? Or would it feel like bad news? An ending that closes in on itself, rather than one that fades quietly away? I am curious which one your gut chooses first. Tell me in the comments. There is no wrong answer, only what you feel. And now take another slow breath, because we have named the force. We have named the mystery. We have watched the old ending crack in front of us, and the new hints of evolution rise up in its place. But we have not, yet, walked through the endings that this uncertainty opens up. We have not looked at them one by one. We have not felt what each of them would actually be like if it were true. That is what we are about to do. We are going to walk through 5 possible endings of the universe. 5 doors. 5 long corridors leading away from the moment you are sitting in right now. Some of them are slow. Some of them are violent. Some of them are cyclical. And one of them is so quiet, so instantaneous, that if it began right now on the far side of the cosmos, you would never see it coming. It would be here before the news of it could reach you. So let's open the first door. The first door is the quietest. It has no drama in it. No violence, no fire, no collapse. It is in many ways the ending that most cosmologists working today would still tell you is the most likely. The one that fits our best current data, the one that emerges naturally from Einstein's equations, if dark energy is roughly what we thought it was for the last 2 decades. It is the ending we call the Big Freeze, or in its more technical name, the heat death of the universe. And to walk through it, we do not need explosions. We just need patience, an unimaginable amount of patience. Picture the cosmos right now as you know it. Galaxies scattered across the sky like grains of sand in an enormous ocean. Each galaxy is a swirl of billions of stars. Each star is a furnace, quietly turning hydrogen into helium, throwing light and warmth into the surrounding void. Some of those stars have planets. A few of those planets, we think, have living things on them. And all of it is bathed in the faint, ancient afterglow of the Big Bang, a nearly uniform hum of microwave radiation, the leftover heat of the moment when the universe first became transparent to light. Now press forward, slowly. Watch the galaxies drift apart, not toward anything, just outward. Watch the great cosmic web, the vast filaments of dark matter and gas that thread the universe together, grow more attenuated, more stretched, more diffuse. Watch the space between everything get larger and larger. And watch, most importantly, the temperature drop. Because that background hum of the Big Bang, that ancient microwave glow, is cooling as the universe expands. It is nearly 3 degrees above absolute zero today. In the far future, it becomes 2, then 1, then 1/10 of a degree, then 100th, then 1,000,000th. The sky, quite literally, is growing colder. And in that slowly cooling sky, the stars begin to disappear, not suddenly, not dramatically, just a few at a time. The big, bright, hot ones burn through their fuel first. Blue giants live for only a few million years, which sounds like a lot until you place it against the age of the universe. Then the medium-sized stars like our sun, burn through their hydrogen over billions of years, swell into red giants, shed their outer layers, and leave behind slowly cooling embers called white dwarfs. Then the small stars, the patient ones, the red dwarfs, keep going. They are frugal. They burn slowly. Some of them have enough fuel to last for trillions of years. And when the last of them finally runs out, somewhere between 100 trillion and 1,000 trillion years from now, something quiet happens to the universe. The lights go out. Not just for a moment, not just in one place, everywhere, all at once on cosmic time scales. The last new star finishes forming. The last old star finishes fading. And the universe, for the first time in its entire history, is dark. There are no fires anywhere. There is no new light being made. There is only the faint, dying glow of stellar corpses, white dwarfs slowly cooling, neutron stars slowly cooling, and the cold, empty voids between them. That is the end of the stelliferous era, the era of stars. The era we are living in right now. We tend to think of the star-filled universe as the ordinary state of things, because it is the only state of things we have ever known. But in the long history of the cosmos, the stelliferous era is a brief, bright, flickering moment, a candle that is already, in cosmic terms, halfway burned down. That is the big freeze in outline, slow, cold, silent. Not really an ending at all in the traditional sense, more like a fading, a dispersal, a universe that gets so thin, so cold, so quiet, that eventually there is nothing left doing anything. But we will come back to the big freeze in much more detail later tonight. Because when you walk further down that road, past the death of the stars, past the death of the galaxies, past the death of matter itself. You find eras stranger than almost anyone ever tells you about. Eras that dwarf everything else. That is coming. For now, close that first door and open the second. The second door does not close quietly. It tears. This is the ending we call the Big Rip. And it is what happens if the dark energy we talked about, the mystery force pushing the universe apart, is not constant and not weakening but strengthening, growing more violent over time. Physicists have a name for a hypothetical dark energy that behaves this way. They call it phantom dark energy. The name is meant to sound a little unsettling because it is a little unsettling. Phantom dark energy is the version where the outward push of the vacuum does not merely persist, it accelerates its own acceleration. It gets stronger and stronger until, eventually, it overwhelms every other force in the universe. Imagine watching that in slow motion. At first, nothing looks different. The galaxies drift apart as they have for billions of years. Then, gradually, the drift becomes a rush. Distant galaxies, which used to be visible through telescopes, redshift so severely that their light can no longer reach us. The sky, one galaxy at a time, empties out. Then, closer to home, the great cluster of galaxies we belong to, the local group, containing our Milky Way, Andromeda, and dozens of smaller companions, begins to feel the force. Even it, held together by gravity for billions of years, begins to unravel. Andromeda, which was on a collision course with the Milky Way, is instead pulled away from us, then farther, then gone, and then it gets closer. The push begins to reach into the galaxy itself. The spiral arms lose their coherence. The stars in the outer edge of the Milky Way drift away, no longer bound. The center loosens, faster now, faster than gravity can hold anything together. Solar systems, which have circled their stars for billions of years in stable, patient orbits, feel the push begin to overwhelm the pull. Planets spiral outward, away from their stars into the growing dark. Then the push reaches into the atom. This is the strangest part of the Big Rip. When phantom dark energy grows strong enough, it does not merely stretch space. It stretches everything inside space. The electromagnetic forces that bind atoms together, the strong nuclear force that holds the nucleus, the delicate architecture of every molecule, all of it begins to lose the tug of war against the outward pressure. In the final moments, atoms themselves are torn apart, then nuclei, then possibly the elementary particles inside them. Everything is pulled outward faster than it can hold itself together. And then space, in a mathematical sense, tears. The distance between any 2 points, no matter how close, goes to infinity in a finite time. That is what makes the Big Rip so eerie. It has a date. Some versions of the model, based on certain values of phantom dark energy, place it as soon as 22 billion years from now younger, at the moment of the tearing, than the universe is right now. It is not a slow death by cold. It is a screaming, everywhere at once unraveling of the very fabric of reality. But now, in fairness, because we are trying to be honest tonight, The Big Rip requires dark energy to behave in a very specific, quite extreme way. Most observations, including DESI's, do not currently favor phantom dark energy. If dark energy is fading, as the newest hints suggest, then the Big Rip becomes less likely, not more. It is a possibility, not a prediction. But it is a possibility real enough that, for 2 decades, physicists have taken it seriously. Because it is what happens if the mystery force we do not understand turns out to be even stranger than we already think it is. Close the second door and open the third. The third door is the mirror. This is the ending we call the Big Crunch. It is, in a sense, the ending we were promised as children, the one where the universe folds back into itself, where the expansion reverses, where the galaxies come rushing home. For 27 years, we thought the Big Crunch was dead. We thought the discovery of accelerating expansion had killed it forever. But if dark energy is not truly constant, if the recent DESI hints hold up and dark energy is weakening, then the Big Crunch, quietly, is walking back into the room. Here is how it would go. Right now, dark energy is winning the tug of war against gravity. The expansion accelerates. But if dark energy is fading, if its outward push weakens over billions of years, then eventually gravity catches up. The expansion slows, then stops, then delicately begins to reverse. The galaxies that have been drifting apart begin, imperceptibly at first, to drift back toward each other. The distances between them shrink. The cosmic microwave background, which had been cooling for billions of years, begins for the first time to warm, and then it accelerates. Because gravity, once it starts to win, is patient but relentless. The universe falls inward. The galaxies collide, merge, become dense clusters, become superclusters, become eventually one crowded, incandescent mass. The temperature of empty space, which had been near absolute zero, begins to rise. Then it rises faster. The night sky itself grows warm, then hot, then blindingly bright. All the light from every star and every galaxy, blue-shifted by the collapse, floods the cosmos with radiation. Every direction you look, in every part of the sky, is fire. And in the final moments, everything, every atom, every particle, every photon is squeezed together into a single point of unimaginable density. A singularity, the mirror of the Big Bang, an ending that looks, quite literally, like the beginning, run in reverse. That is the Big Crunch. And what makes it so haunting is that it looks, at first glance, like the neat textbook ending you were taught as a child. But now, if it happens, it will happen not because gravity was always going to win, but because the strange, invisible force pushing the universe apart quietly ran out of energy. It would be an ending that arrives late. An ending that arrives only because the outward push finally sighed and let go. Close the third door and open the fourth. The fourth door is the one that does not close at all. This is the big bounce. It is the ending that is not really an ending. In the big bounce, the collapse of the Big Crunch does not truly reach a singularity. Instead, at the moment when the universe becomes small enough, hot enough, dense enough, some new physics, some quantum effect we do not yet fully understand intervenes. And instead of collapsing into a single point, the universe bounces, rebounds, explodes outward again into a new Big Bang, and begins again. In the Big Bounce, our universe is only one loop in a longer cycle. There may have been many before ours. There may be many after. Each one born from the collapse of the last. Each one carrying, perhaps, faint echoes of what came before, or perhaps nothing at all, a clean slate every time. Cosmologists have flirted with cyclic cosmology for decades, and in recent years, versions of it have become surprisingly serious. Some models tie the bounce to a fading dark energy that eventually reverses. Others tie it to a colliding brain scenario from string theory. Others still, including the conformal cyclic cosmology proposed by the Nobel laureate Roger Penrose, suggest that the far, cold, empty future of a heat-dead universe becomes, mathematically, indistinguishable from the fiery beginning of a new one. That last idea is worth pausing on because we will return to it. But in the Big Bounce, in whatever version, the ending is not truly an ending. It is a handoff, a turning of a page. The story continues on the other side of what looks, from the inside, like the last moment of everything. There is no death in this ending. There is only rebirth. Close the fourth door and open the fifth. The fifth door is different from all the others. Because the first four endings happen slowly. They happen over billions, trillions, quintillions of years. You would have time to see them coming, time to say goodbye, time to make peace with them. The fifth door does not give you that. The fifth door is the one we call vacuum decay, or more evocatively, the Big Slurp. And to understand it, we have to remember something we said earlier, that our best theories of physics suggest empty space itself has energy, that the vacuum is not truly empty, that there is a kind of underlying field everywhere that quietly holds the universe together with all its familiar laws. Now, here is the unsettling question. What if our vacuum is not the most stable state possible? Physicists have a name for this. They call our current vacuum a false vacuum. The idea is that there might be another, deeper, lower energy state, a true vacuum, that the universe could, in principle, fall into. Between us and that true vacuum is an energy barrier. Ordinarily, that barrier is enough to keep us where we are. But in quantum mechanics, particles and fields can occasionally tunnel through barriers they should not be able to cross. And if, somewhere in the vast expanse of the universe, a tiny bubble of true vacuum happens to nucleate, happens by pure quantum chance to form, that bubble does not stay small. It expands. It expands at the speed of light. And inside the bubble, everything is different. The laws of physics themselves are different. The masses of particles change. The forces reorganize. Atoms as we know them cannot exist. Chemistry as we know it cannot exist. Anything that was inside the bubble at the moment it swept through is simply gone, rewritten, erased into something else. And because the bubble expands at the speed of light, you cannot see it coming. No warning signal can travel faster than the wave itself. If a bubble of true vacuum formed right now on the far side of the Milky Way, it would arrive at Earth in about 100,000 years, and we would have no way of knowing until it did. If it formed closer, we would have less. If it formed right next to you, right now, this instant, you would not have time to finish the thought. This might sound like pure science fiction, but it is not. Physicists have taken vacuum decay seriously for decades, and in the last few years, something extraordinary has happened. Researchers in Italy, in the United Kingdom, and in China have started to build tabletop analogs of vacuum decay in the laboratory. They cool clouds of atoms, sodium atoms, in one case, to within a millionth of a degree of absolute zero, tune the atoms into a metastable configuration that mimics a false vacuum, and then watch in real time as bubbles of the true state nucleate and spread. It is not, of course, the real vacuum of our universe. It is an analog, a shadow, but it is the first time we have ever watched, in the real world, the physics of false vacuum decay play out in front of our eyes. Those experiments have been published in Nature Physics and Physical Review letters over the last 2 years, and they represent the first empirical grounding of a theory that used to live entirely in equations. And here is the piece of the picture that keeps some physicists up at night. When we measure the mass of the Higgs boson, the famous particle discovered at the Large Hadron Collider in 2012, we get a value of about 125 gigaelectron volts. When you plug that number into the standard model of particle physics, along with the mass of the top quark, and ask, is our vacuum stable? The answer is not a clean yes. The answer is probably metastable, meaning that our vacuum is stable enough to have lasted nearly 14 billion years, but not, according to the math, stable forever. The half-life for vacuum decay in the most conservative estimates is something like 10 to the power of 139 years, a number so vast it makes the age of the universe look like a blink. So in practice, it is not going to happen anytime soon. Almost certainly not in the next trillion years, but the possibility is there. It is a real feature of our current best physics, and if we ever discover new particles or new physics that shift the calculation, the timeline could shift too. That is the fifth door. The one that closes without warning, the ending that does not announce itself, the ending that, if it ever happens, has already happened by the time you would know. 5 doors, 5 endings, the slow freeze, the violent rip, the mirror crunch, the endless bounce, and the silent bubble. Remember, at the very beginning of tonight, we said the ending you were taught was a lie. Now you see why. There is not one ending. There are, at minimum, 5. And the honest, humbling truth is that our best current physics does not yet tell us with certainty which one is ours. Some are more likely, some are less. The freeze is currently the front runner. The rip has faded a little with the DESI results. The crunch has quietly returned. The bounce is speculative but real. The vacuum decay is remote but real. Any of them could be the ending we are inside of, right now, tonight. So before we walk further, I want you to sit with all 5 of them for a moment. Feel them in your mind. And then tell me honestly in the comments, of these 5 endings, the slow freeze, the violent rip, the mirror crunch, the endless bounce, and the silent bubble, Which one unsettles you the most? Which one, when you imagine it, makes your chest tighten a little? And stranger question, which one, when you imagine it, oddly comforts you? Because I promise one of them will. There is always one. Tell me which. And now take another slow breath. Because of these 5 endings, one of them stands, according to our best current understanding, as the most likely fate of our cosmos. The slow freeze, the quiet fade, and so far we have only stood at its doorway. We have only glimpsed the first hallway inside it, the death of the stars, the end of the stelliferous era, the going out of the lights. But past that hallway the road stretches on, and on, and on, into eras so long, so vast, so patient, that the entire age of the universe up to today becomes a single, forgotten instant. There are things that happen in the deep future that no textbook ever told you about. Things that unfold after all the stars are gone. Things that unfold after all the matter is gone. Things that unfold after even the black holes are gone. We are going to walk down that road together, all the way to the end. So let's take the first door back off its hinges. And let's step through into the long dark. Take a moment before we begin to steady yourself. Because the road we are about to walk is not measured in the units you are used to. It is not measured in years. It is not measured in millions of years or even billions of years. It is measured in eras. And each era in this deep future is not a little longer than the one before it. It is 10 times longer, sometimes 100 times longer. Sometimes a trillion times longer. The scales grow so fast that if you tried to draw them on a normal ruler, the era we live in, the entire lifetime of every star that has ever existed in the visible universe, would be too small to see. A dot, a pinprick, a single forgotten atom of time. We are going to walk from that pinprick gently all the way to the end. There are 5 eras in the standard picture of the deep future. Cosmologists sometimes call them together the ages of the universe. Fred Adams and Gregory Laughlin, in a famous paper in the late 1990s and later in their book The 5 Ages of the Universe, laid out the framework we still use today. The primordial era, the stelliferous era, the degenerate era, the black hole era, and the dark era. Each one, by definition, at least 10 times longer than the last, most of them far more. We have already passed through the first one, the primordial era. That was the moment just after the Big Bang, before any stars had formed. A hot, dense, chaotic infancy lasting a few 100,000 years, a rounding error in the long story. And right now, tonight, at this very moment, you are living inside the second era, the stelliferous era, the era of stars. It is worth stopping to feel that. Because you are inside the brightest chapter of the entire cosmic story. The one and only chapter in the whole long book in which the sky is full of fires. There has never been a time before this era when stars shone in the way they shine now. And there will never be a time after this era when they shine again. Right now, tonight, in this small window, you are standing inside the age of light. Everything you have ever seen with your eyes has been a gift of this era. And the era is already, quietly, running down. The stelliferous era is expected to last from roughly the first 100 million years after the Big Bang, when the first stars began to form, until somewhere between 100 trillion and 1,000 trillion years from now. That is when the last stars go out. Let those numbers sit for a moment. The universe is about 13.8 billion years old today, 13.8 billion, and the stelliferous era might last from beginning to end 1,000 trillion years. That means we are, right now, less than 1% of the way through the age of stars. Less than 1%. If the stelliferous era were a single day, our position in it would be somewhere around midnight, at the very first minute of the very first hour. The morning has not even started. Nearly all of the light this universe will ever produce still lies in front of us, but it does not last forever. Here is what happens. Over the next few billion years, the biggest, hottest stars keep burning out fast. That is what they have always done. Blue giants live briefly. Yellow stars, like our sun, live for around 10 billion years and then swell into red giants, blow off their outer layers, and shrink into slowly cooling embers we call white dwarfs. In about 5 billion years, that is exactly what our sun will do. The Earth will not survive it, neither will Mars. The inner solar system will be scoured into ash by a bloated red star, and what remains will orbit, silent and dark, around a slowly cooling coal at the center. That is the fate of our own home, and it is barely the beginning. The medium-sized stars keep dying, era after era, and meanwhile, new stars are still being born out of the leftover gas of dying ones. This has been going on for nearly 14 billion years. But the raw material, the free hydrogen from which stars are made, is being slowly consumed. Every time a star forms, it locks up gas in its core. Every time a star dies, it recycles some, but not all, of that gas back into the interstellar medium. The recycling is imperfect. Bit by bit, more and more of the universe's hydrogen becomes locked into remnants that no longer shine. So the birth rate of stars slows, and slows, and slows. By about 100 trillion years from now, if you were floating in what used to be a galaxy, you would find that no new stars are being born at all. The hydrogen has run out. The star factories have gone silent. The only stars left burning are the smallest, most patient of them, red dwarfs, cool little embers, some of which can burn for trillions of years on a single tank of fuel. But even they eventually, one by one, will fade. And in the last flickers of the stelliferous era, a lonely observer would see, across the darkening sky, the final red dwarfs winking out. Not all at once, not with any grandeur, just quietly, each one in turn running out of what it was made to burn. And then, somewhere between 100 trillion and 1,000 trillion years from now, the last star goes dark. Imagine, gently, being there for it, floating in the outer edge of a galaxy that no longer contains any active fires. The sky around you is not black, not yet. The old white dwarfs still glow faintly, in a color they call black-body red, a color so dim it is almost invisible to human eyes. There are neutron stars, still radiating a little heat. There are brown dwarfs, failed stars that never quite lit up, still holding a tiny amount of warmth from their formation. The galaxy is a graveyard of glowing corpses, but no new light is being made anywhere. The universe has, for the first time in 100 trillion years, stopped shining. That is the boundary. That is when we cross from the stelliferous era into the degenerate era. And here is where the scale begins to break your mind. Because the stelliferous era lasted, at most, 1,000 trillion years, a number that already dwarfs everything human, and the degenerate era lasts something like 100 million trillion years. Written out, that is a 1, followed by 26 zeros. Written more compactly, 10 to the 26th, and that is only its middle. Some estimates stretch the degenerate era all the way out to 10 to the 40. If the stelliferous era, at 1,000 trillion years, is the first inch on your ruler, then the degenerate era, at 10 to the 40th years, is a ruler as long as 10 to the 25th stelliferous eras stacked end to end. The age of stars becomes a rounding error in the age of stellar corpses. Take a slow breath with that, because that is the true scale of the cosmos. So what happens during the degenerate era? What fills all of that vast, vast time? Very slow, very quiet things. Cooling. Drifting. Occasional, extremely rare collisions. Every few tens of millions of years in the early parts of this era, two brown dwarfs might, by pure chance, drift into each other. If their combined mass is high enough, they can briefly ignite, becoming a new star for a few million years. A tiny, brief reignition of light in a universe otherwise gone dark. These events are called stellar collisions, and by the middle of the degenerate era, they become the only source of visible light left anywhere in the cosmos. Rare little candles, lit for a moment, in the middle of an ocean of night that lasts trillions upon trillions of years between them. Meanwhile, galaxies themselves begin to unravel, not dramatically. Just over enormous stretches of time, the stellar remnants inside a galaxy have gravitational interactions with each other. Sometimes a remnant is flung outward, ejected into intergalactic space. Sometimes it spirals inward, toward the supermassive black hole at the galactic center. Over the course of 10 to the 19th or 20th years, most of the objects in a galaxy either evaporate into the void or are consumed by the central black hole. The galaxies themselves, as recognizable structures, quietly dissolve. And then, deep inside the degenerate era, something even stranger is expected to happen. Something that reaches into the very fabric of matter itself. Protons begin to decay. The proton, as far as we know, is one of the most stable objects in the universe. It sits at the center of every atomic nucleus. Every atom of hydrogen, every atom of oxygen, every atom in your body is built around a small collection of protons and neutrons. And for as long as physics has been studied, the proton has been assumed to be permanent, eternal, unbreakable. But most modern theories of physics, most grand unified theories in particular, predict that the proton is not truly eternal. It is merely extremely long-lived. The prevailing estimate for its half-life is somewhere around 10 to the 34th years. That is, 1 followed by 34 zeros. That is a number so vast that in the entire history of the observable universe so far, only the tiniest fraction of protons should have decayed. We have never directly observed a single proton decaying, despite watching enormous tanks of water underground for decades. But if the theories are right, they will. And when they do, matter itself begins to unravel. Inside a white dwarf, over unimaginably long stretches of time, protons begin to fall apart, one by one. Each decay releases a tiny burst of energy, a positron, a pion, a smattering of radiation. It is estimated that each white dwarf, powered by this trickle of proton decay, radiates about 400 watts of energy, roughly the power of a bright household light bulb. And that 400 watts, spread across the enormous surface area of an entire star, produces a glow so faint you would never see it. But it is there. In the deep dark of the degenerate era, white dwarfs shine, ever so slightly, powered not by nuclear fusion but by the slow decay of their own protons. They are burning themselves, literally, and atom by atom they disappear. Over 10 to the 34th years, half the protons in a white dwarf are gone. Over 10 to the 40th years, essentially all of them. What was once a star's worth of matter has quietly, patiently, evaporated into radiation. Neutron stars follow the same slow fate. Planets cold, silent worlds orbiting long-dead suns decay too, atom by atom, until they cease to exist as coherent objects. By the end of the degenerate era, essentially all of the ordinary matter in the universe, every atom of every star, every planet, every particle of dust is gone. Not scattered, not dispersed, gone, decayed into light, into leptons, into the faint hum of low-energy radiation. Everything you know as solid, as tangible, as real, every book, every mountain, every ocean, every body has in this future ended not with a shattering, but with a slow, patient forgetting. We should pause here, because this is one of the strangest and most humbling moments in the entire long story. Everything you have ever touched, everything that has ever built any structure or thought any thought, is made of atoms, and atoms are made of protons. And if the current best theories are right, protons themselves are not eternal. They are only long. In the deep future, matter as an idea, matter as the substance from which things are made, is a temporary phase in the cosmos. It is a chapter, not a permanent feature. Long, yes, almost incomprehensibly long, but finite. Call back to that flat cartoon diagram from your childhood, the trumpet-shaped cone stretching from Big Bang to some clean, tidy ending. Remember it. This is what it was hiding. This is what was outside the frame. An era so long, so slow, so patient, that the entire history of stars and galaxies and life is nothing more than a bright morning at the beginning of a very long day. And we are still not at the deepest part. Because after the degenerate era, after essentially all the matter is gone, one kind of object remains, and it dwarfs everything before it, everything. We cross into the black hole era. The black hole era begins somewhere around 10 to the 40th years after the Big Bang, and it lasts, by most estimates, until 10 to the 100th. Let me try to give you a sense of what that means. 10 to the 100th, 1 followed by 100 zeros. That number has a name. It is called a googol. It is the number the search engine Google was named after. And it is a number so large that if you were to try to write it out as a series of one-year ticks on a timeline, and each tick was smaller than an atom, the timeline would still be far, far longer than the observable universe is wide. It is a number that has no physical analog. There is nothing in your experience to compare it to. It simply is. And for that unimaginably long span, this is what the universe looks like. Black holes. Nothing but black holes. Some of them stellar mass, the collapsed corpses of what used to be big stars. Some of them intermediate. Some of them supermassive, the great gravitational monsters that used to sit at the centers of galaxies, now floating alone in an ever-emptier void. And around them, essentially nothing. A thin bath of extremely dilute radiation. A few stray particles from proton decay drifting through the immense dark. No stars, no planets, no matter, just black holes, silent and vast, drifting apart in an expanding sky. And this is the era in which one of the strangest, most beautiful, and most humbling processes in all of physics gets to run its full course. The evaporation of black holes. For most of scientific history, black holes were thought to be forever. They were the endpoints, the graves, the final destinations. Anything that fell in never came out. But in 1974, a young physicist named Stephen Hawking, drawing on quantum field theory near the event horizon of a black hole, proved something that no one had expected. Black holes are not truly black. They radiate. Very, very faintly, very, very slowly, in a way that had never been predicted before. What Hawking realized is that, at the edge of a black hole, right at the event horizon, the point of no return, the quantum vacuum is doing what quantum vacuums always do. Pairs of virtual particles are constantly appearing and disappearing, flickering in and out of existence in the ordinary quantum foam of empty space. Normally, they annihilate each other before they can be observed. But right at the event horizon, sometimes, one of the pair falls in and the other escapes. The particle that escapes carries away a tiny, tiny bit of energy. And by the strict conservation laws of physics, that energy has to come from somewhere. It comes from the black hole itself. The black hole loses a sliver of its mass. This is Hawking radiation. And it is extraordinarily slow. For a black hole with the mass of the sun, the Hawking radiation is so faint that its temperature is 100 million times colder than the coldest thing ever measured in a laboratory. So faint that today, in the current universe, the black holes we know about are absorbing far more energy from the cosmic microwave background than they are emitting through Hawking radiation. They are not evaporating yet. They are still growing, ever so slightly. But in the deep future, once the cosmic microwave background has cooled to below the Hawking temperature of a black hole, the balance flips. The black hole begins to radiate more than it absorbs, And once that happens, it begins, over unimaginable spans of time, to shrink. The rate of evaporation depends on the size. A small black hole evaporates faster. A large black hole evaporates slower. For a stellar mass black hole, say, one with the mass of a few suns, the total time to evaporate completely is around 10 to the 67th years. Let that number sit for a moment. 10 to the 67th years. That is a 1 followed by 67 zeros. It is a duration so vast that if the current age of the universe were compressed into a single second, 10 to the 67th years would be nearly 200 trillion times the age of the universe. And that is only for a stellar mass black hole. The bigger black holes take much, much longer. For the supermassive black holes at the centers of what used to be galaxies, with masses of billions of suns, the evaporation time stretches out to around 10 to the 100th years. A Google. The longest naturally occurring timescale in the known cosmos. Try to picture that. Try to feel that. Try to imagine what it would mean to sit as a witness, somehow, at the center of a universe in which nothing else exists, and watch a single supermassive black hole slowly, silently, over a Google years, radiate itself away into a bath of nearly frozen photons. There would be no other events. Nothing else would happen. There would be no sound because there would be no medium to carry sound. There would be no light because there would be no visible light photons. Just an immense, dark, expanding void. And somewhere in it, the faintest imaginable glow of a black hole in its final, patient death. And the death, when it comes, is not quiet, because as a black hole evaporates, it shrinks. And as it shrinks, its Hawking temperature rises, faintly at first, then more, then more. And in the final moments of a black hole's life, once its mass has fallen to the level of a mountain, the temperature climbs rapidly. Once its mass reaches the level of a boulder, it climbs faster. Once its mass reaches the level of a grapefruit, it is glowing white-hot in gamma rays. And in the last fraction of a second, the very last flicker, the black hole releases the remainder of its mass in a burst of high-energy radiation as bright as a small supernova, a flash, in the deep dark, after a Google years of silence, and then nothing. That is how black holes die. Not slowly, not gently, with one final, sudden, dazzling flash, the last new event perhaps in the entire history of the universe. And after that flash, in the region where the black hole used to be, there is only the thin outgoing wave of its own radiation, dispersing into an empty sky. By the end of the black hole era, every black hole in the universe, every stellar remnant, every galactic monster has done this. Every one of them has flashed. Every one of them is gone. And what is left in the entire immense expanding cosmos is a nearly perfectly uniform bath of extremely low-energy photons, drifting through an expanding void that is, by now, unfathomably vast. A few electrons and positrons here and there, a trickle of neutrinos, otherwise nothing. We cross into the dark era. The dark era is defined, roughly, as everything that happens after 10 to the 100th years. It does not have a clear end. It may not have an end at all. It is the longest, quietest era in the cosmos, and in a very real sense, it is where the universe finishes forgetting itself. There are no stars, there are no planets, there is no matter, there are no black holes. There is only a thin, cold, ever-diluting soup of radiation and stray particles, expanding into a space that grows larger every moment, even though there is essentially nothing left in it. Occasionally, over spans of time that dwarf everything we have already talked about, a passing electron might encounter a passing positron and briefly form a strange, huge, extremely faint atom called positronium, an orbit between a particle and its antiparticle, before annihilating into a couple of photons. Those photons drift away, redshifting into oblivion. That is the entire drama of the dark era. That is all that happens, and it goes on, and on, and on, forever as far as we know. There is no clock in the dark era because there is nothing left doing anything at a regular rate. There are no seasons, no cycles, no processes. Time, in the operational sense, time as change, has come as close to stopping as it can without literally ending. Call back one last time to the flat cartoon diagram in the science textbook. Remember it, the one you saw as a child. That diagram had a small dot on the left, a swirling middle, and a clean edge on the right. What we have just walked through together is what was outside the right side of that page, what was never drawn, what no textbook could have captured, because there is no way to fit a Google years onto a piece of paper. The ending of the universe at its truest scale is not a moment. It is not an event. It is not a bang, and it is not a whimper. It is a length of time so vast that everything we call history, every star, every civilization, every love, every loss, every note of every song ever hummed, happens in the first breath of the first minute of the first hour of an infinitely long, cold, quiet dawn. And you are inside it, right now. In the brightest, briefest moment of it. Take a slow breath because we need to sit with that. And now, honestly, tell me something. When you imagine yourself as a witness at the end of the stelliferous era, 100 trillion years from now, hovering somewhere in the outer dark, watching the very last red dwarf finally flicker and go out, what do you feel? Loss, grief, a strange peace, a calm you did not expect. What does your mind actually do when it tries to hold a time scale that large? I am genuinely curious. Tell me in the comments what came up for you. And now, take another slow breath. Because you might think, after all of that, after the death of stars, after the death of matter, after the death of black holes, that we have reached the bottom of the story, that we have finally arrived at the ending, that there is nothing left to say. But we haven't, not quite, because when you sit for long enough with a universe that does not really end, but instead just slowly, patiently forgets itself, a question begins to whisper underneath everything. A question that quietly dissolves the meaning of the word ending itself. If nothing changes, does time still pass? If there is no clock, is there a future? And if the far, cold, empty future of a heat-dead universe looks, mathematically, indistinguishable from the fiery beginning of a new one, then have we really described an ending at all? Or have we, without knowing it, described a handoff? That question is where we go next, and it is where the very idea of an ending begins to come apart in our hands. There is a strange thing that happens when you stare at the dark era for long enough. A thing that quietly unmakes the question you started with. Because when you first hear the phrase, the end of the universe, your mind imagines a moment, a last instant, a final second on some cosmic clock after which nothing happens, a door slamming shut, a curtain falling. A last frame of a film held for a heartbeat and then black. But that is not what the dark era is. The dark era is not a moment. It is not a last frame. It is not an ending in any sense that a human being is built to understand. It is a condition, a state, a quality of the universe in which nothing new is happening, nothing is changing. Nothing is heating or cooling or moving or flashing or forming. It is the universe in a state of maximum disorder, which is a phrase physicists use with a very specific meaning. When we say maximum disorder, we do not mean chaos in the everyday sense. We mean that every part of the universe is as spread out as it can be. Every particle is as far from every other particle as it can get. Every temperature has averaged out with every other temperature. There is no gradient anywhere. There is no hot and cold. There is no here and there. There is nothing left to flow from anywhere to anywhere else. And here is the strangeness. In physics, time, the actual physical passage of time, not the abstract idea of time, is deeply tied to change. It is tied to the movement of things from more ordered states to more disordered states. That is what the second law of thermodynamics is telling us. Every process at every scale tends to increase the total disorder of the universe. That is why heat flows from hot to cold, never the other way. That is why an ice cube melts in your drink and does not spontaneously reform. That is why time, in every experiment we have ever done, points in one direction from order toward disorder. The physicist Arthur Eddington gave that direction a name. He called it the arrow of time. And in the dark era, that arrow has, for all practical purposes, been used up. There is no more order left to spend. There is no more energy that can move from one place to another and cause a change. There is no more heat that can flow. The universe has done all the changing it can do. And so, in a sense, we have not yet had the courage to say out loud, time has ended too. Not because some cosmic clock has struck a final hour, but because there is nothing left anywhere to distinguish one moment from another. Ask yourself quietly, if nothing happens between one moment and the next, what does the phrase one moment and the next even mean? In the dark era, that question has no answer. Every second is the same as every other second. Every century is the same as every other century. Every Google years is the same as every other Google years. There is no way to tell them apart. There is no experiment that could distinguish them. There is no observer that could remember them because there are no observers left. There is only a thin, cold, quiet field of particles and photons spread across an unimaginable void, and from the inside, no way to know how long that field has existed. It could have been there for a moment. It could have been there for 10 to the 10,000th years. There is no difference. There is no way to feel one. Take a slow breath with that, because that is a strange, strange thought. The universe does not end with a bang. It does not end with a whimper. It ends by becoming a condition in which the very idea of ending has no meaning left. And this is where cosmology begins to bleed, quietly, into philosophy. Because if there is no way from the inside to tell a nanosecond from a Google years, then in what sense does the universe last for a Google years at all? Or, to put it more strangely, in what sense does it last for any finite amount of time? What if the far, quiet future of the cosmos is not truly a length of time at all, but a kind of timelessness, a stillness so complete that any duration we assign to it is a story we tell ourselves from the outside? Some physicists have taken this idea very seriously, and one of them, a Nobel laureate named Sir Roger Penrose, has taken it further than most. Penrose looked at the dark era and asked a question that, at first, sounds almost absurd. He asked, what does the dark era look like from the inside? Not to a human being, there are no human beings there, but to the physics itself, to the equations. What does an infinite, expanding, thermal soup of massless particles actually resemble mathematically? And the answer he came to is astonishing. It looks mathematically exactly like the very beginning of another universe. Here is why. In the dark era, all matter is gone. The only things left are photons and possibly a few very low-mass particles like neutrinos and their remnants. Objects that, from a certain perspective, effectively have no mass at all. And in a universe made of only massless things, there is a strange property that emerges. Scale, the very idea of size, stops mattering. A universe made of only massless particles has no ruler in it, because you need mass to define a ruler. Without mass, there is no way for the universe to tell whether it is enormous or tiny. The idea of distance itself becomes ambiguous. The physics becomes what mathematicians call conformally invariant, which is a technical way of saying that stretching or shrinking the whole universe leaves the physics unchanged. Now, look at the Big Bang. Really look at it. In the first tiny fraction of a second after the Big Bang, the universe was so hot, so dense, so violently energetic that all the matter in it was effectively massless. Particles moved at or near the speed of light. Mass, as we understand it, had not yet emerged. The universe was, in the mathematical sense, conformally invariant. Penrose noticed the parallel. The universe at the very beginning, before mass, and the universe at the very end, after all the matter is gone, share the same mathematical structure. From the inside, in a deep sense, they are indistinguishable. And if you accept a certain reading of the math, a reading Penrose calls conformal cyclic cosmology, then those two states are not merely similar. They are, in a real sense, the same state. The end of one universe becomes, seamlessly, the beginning of another. The dark era of ours is the Big Bang of theirs. There is no transition. There is no crossing. There is only the mathematical fact that after long enough, the ending forgets itself so completely that it looks exactly like a beginning. Penrose has been laying out this idea for over 15 years now in a series of books and papers. It remains controversial. It is a hypothesis, not a proven fact. We should be honest about that. Some of his colleagues, physicists whom he respects and who respect him back, remain skeptical. The evidence he has offered for cyclic patterns in the cosmic microwave background is contested. His interpretations are debated. This is not settled science. It is one physicist's attempt to look at the dark era and ask, with mathematical rigor, whether the ending really is an ending, or whether it is merely a very long fade into another beginning. But whether or not you find Penrose's specific version convincing, the deeper thought behind it is worth sitting with, because it points at something almost no one tells you when you are first told the story of the universe. The very concepts we use to describe endings, moment, duration, before, after, last, first, are concepts borrowed from finite lives. They are concepts invented by beings who die. They fit us. They fit our stories. But there is no guarantee they fit the cosmos itself. The universe never learned the word end. It only does what it does. And what it does in the deep future might be nothing that a human word was ever built to capture. And there is another wrinkle here, one that is even stranger, and one that has crept into serious cosmology only in the last few decades. What if our universe is not the only one? Now, we have to be careful with the word multiverse. It has been so overused in popular culture that it has almost lost its meaning. But in physics, the word refers to specific, precise ideas that arise, unforced, out of some of our best current theories. The one most relevant to us tonight is called eternal inflation. Eternal inflation is a proposal originating in the work of Alan Guth, Andre Lind, and others in the 1980s and 1990s, that the very rapid expansion which drove the birth of our own universe, a period we call cosmic inflation. In the first fraction of a second after the Big Bang is not a one-time event. In many versions of inflation, the process, once started, never truly stops. It continues everywhere forever in what we might call a vast inflating background. And occasionally, in some corner of that vast background, inflation ends locally. A tiny region of the inflating field settles into a stable state, into what we would recognize as a universe like ours, with its own laws of physics, its own particles, its own Big Bang. Our universe in this picture is one of those local pockets, one bubble in an ocean of bubbles, in a background that keeps making more of them forever. And if this is true, then the death of our own universe, whichever ending it turns out to be, is not the death of everything. It is only the fading of one bubble in a foam that keeps producing new bubbles at a rate no observer can even measure, because the parent background is expanding faster than any of us can ever cross. There is, in this picture, no last universe. There is only always more. And this reframes even the most terrifying ending we described earlier, the vacuum decay, the false vacuum, the fifth door that opens without warning. Because in the eternal inflation picture, vacuum decay is not truly an ending. It is a birth. When a bubble of true vacuum nucleates inside a false vacuum and expands at the speed of light and rewrites the physics inside its wake, what has really happened from the outside is that a new region with new laws has emerged, a new universe, a new story. The old one in this reading does not die, it hands off. It becomes the boundary of a new beginning. Think about that for a moment. In the eternal inflation picture, endings and beginnings are not opposites. They are not enemies. They are the two sides of the same event. Every ending is, from the right vantage point, a beginning. Every beginning is, from the right vantage point, an ending of something else. The cosmos in this reading is not a single life that begins, ages, and dies. The cosmos is a process, a continuous transformation, an eternal handing off of the possibility of existence from one region to another, from one set of laws to another forever. And here is where we have to be honest. The eternal inflation picture is not proven. Neither is conformal cyclic cosmology. Neither is any specific cyclic model of the universe. These are hypotheses, well-motivated, mathematically serious hypotheses, but hypotheses. We do not yet have observations that pin any of them down. The far future is still, in many ways, an open question. And any physicist who tells you they know, for certain, what the ending of the universe looks like, or even whether the word ending applies to it, is telling you a story, not a proven fact. But this is the deeper truth we can hold, even in the absence of proof. Every direction we look, from the standard slow freeze through the exotic vacuum decay, through the mathematical strangeness of Penrose, to the runaway foam of eternal inflation, we find the same quiet pattern. The idea of an ending, a clean, final, absolute stop, keeps dissolving under our hands. It does not quite fit. It does not quite hold. The cosmos, whichever door it walks through, does not seem to end so much as transform. It fades. It hands off. It becomes something else. It forgets what it was. And this is where we need to come back to the news from the last 2 years because it matters here. Remember the DESI results. Remember the hint that dark energy may be evolving, may be weakening. If those results hold up, and we should say clearly that they are still hints, not proofs, they change something profound. They do not just tell us that the future may look different. They tell us that the future was never truly fixed. That the parameters we thought were nailed into the equations of the cosmos were not actually nailed at all. That the balance between matter and dark energy, the balance that decides everything, is itself evolving, shifting, alive in a strange sense. If dark energy can change, then the fate of the universe is not something written into the initial conditions of the Big Bang. It is something the universe is deciding slowly as it goes. It is a story still being written, not by any conscious hand, just by the slow evolution of physics that we do not yet fully understand. And that means the ending we described tonight, even the slow freeze, even the 10 to the 100th years of black hole evaporation, even the dark era after, could turn out to be wrong. Not because our physics is bad, but because the universe, as it grows, is negotiating with itself. It is finding out what it is. And we, on our small blue world in the first pinprick of the stelliferous era, are watching it do so with instruments we have only just built. You are alive at a moment in cosmic history when the story of how the universe ends is being rewritten in real time. When the equations are shifting, when the data is arriving, when the researchers themselves are pulling all-nighters and quietly telling each other that our best model of the cosmos may need an update, that is where we are. And when you place that alongside everything we have said tonight, the shifting endings, the dissolving idea of a final moment, the mathematical bridges between the far future and the deep, past the eternal foam of inflation. The possibility that every ending is a handoff. You begin to see something that no textbook diagram ever showed you. There is not one ending. There is not even 5. There is a whole family of endings, each one shading into a beginning of something else. There is a cosmos that does not so much finish as continue. A cosmos that keeps going in some form, in some direction, past every horizon we have ever tried to draw around it. And this, I think, is the strangest and most beautiful realization of the whole long walk we have taken tonight. When we started this video, we were going to answer a simple question. How does the universe end? 2 hours later, we have arrived somewhere we did not expect. We have arrived at the quiet suspicion that the question itself, how does it end, may not be a question the universe knows how to answer, not because it is hiding the truth from us, but because end is a human word, borrowed from human lives, and the cosmos was never built to fit inside it. So let me ask you this honestly, before we take the last step of the journey. If it turns out that our universe's ending is really just another universe's beginning, if endings are just handoffs, if the great cold silence after our own is somehow in some deep mathematical or physical sense the fiery birth of something else, does that thought make you feel more alone in the cosmos or less? Because I think it can go either way. And I am genuinely curious which way it goes for you. Tell me in the comments. I would like to know. And now take one more slow breath, because we are almost home. We started tonight in a classroom, staring at a small diagram that promised a tidy ending. We walked through the death of that ending. We met the invisible force that shattered it. We opened 5 doors, 5 possible fates, and looked gently into each one. We walked, slowly and patiently, through the long dying road of the freeze, from the last star to the last black hole to the still, cold, dark era that has no clock. And now, in the last stretch of this journey, we have watched the very idea of ending begin to dissolve in our hands. There is one thing left, and it is the most important part. It is the moment where we come back, not to the universe, to ourselves. To you, sitting or lying somewhere, wherever you are, in whatever room you are in. To the small, warm, conscious creature listening to this in the middle of a cosmos, so vast it does not remember its own beginnings, and so patient that its ending has no shape a human mind can hold. That is where we go next. And I promise it is gentler than you think. So let's come home, not to any galaxy, not to any era, not to any diagram, just home, to the room you are in right now, to the light around you or the darkness, to the sound of your own breath, moving quietly in and out, as it has been the entire time you have been listening. To the small, warm weight of your own body, resting somewhere at this exact moment. In the middle of a cosmos we have just spent almost 2 hours walking across. Notice how strange it is that you are here at all. Because let's remember gently what we have seen together tonight. We began in a classroom. There was a diagram on the page, a small dot on the left, a widening cone in the middle, a tidy ending on the right, either a mirror of the beginning or a soft fade into gray. That diagram lived quietly in your mind for years. It felt correct. It felt earned. It felt like the shape a universe ought to have. Then we watched it break. We met Edwin Hubble and the redshift of distant galaxies. We met the two teams who chased dying stars across the cosmos in the 1990s and returned with an impossible answer. The universe was not slowing down. It was speeding up. The tidy ending was already gone 3 decades before you learned to draw it. We met dark energy, the invisible pressure of empty space, nearly 70% of everything, and yet a substance we have never seen, never touched, never isolated. A force so strange that our best equations get it wrong by a factor of 10, followed by 120 zeros. And we saw how, for 20 years, we accepted a story about it, that it was a cosmological constant, unchanging, eternal, and how, only in the last 2 years, that story has begun to shift. How the dark energy spectroscopic instrument, with its map of 11 billion years of cosmic history, has whispered the possibility that dark energy may be weakening, evolving, alive in a way we did not expect. How the fate of everything, right now, in real time, is being renegotiated. We opened 5 doors. The slow freeze, the front runner, the ending where the stars simply run out. The violent rip, space itself tearing, atoms unraveling in a screaming everywhere at once collapse. The mirror crunch, the universe folding back into itself, a symmetry of the beginning. The endless bounce, the ending that is not an ending, only a handoff to the next iteration. And the silent bubble, the quiet quantum door that opens without warning, rewriting the physics of everything in its wake. We walked, slowly and patiently, down the long hallway of the most likely one. We watched the last stars go out, sometime between 100 trillion and 1,000 trillion years from now. We watched the stelliferous era end, and the degenerate era begin. We watched matter itself, atom by atom, unbind through proton decay over 10 to the 40th years. We watched the black hole era arrive and last for a googol years, a duration so long that everything that has ever happened before it becomes a rounding error. We watched the last supermassive black hole flash into gamma rays and disappear and leave nothing behind. And then we crossed into the dark era, and we saw together that the dark era is not really an ending. It is a condition. A cold, quiet, still condition in which nothing new is happening, in which the arrow of time has been used up, in which every moment is indistinguishable from every other moment, in which duration itself has lost its meaning. Not an ending, but a forgetting. Not a full stop, but a slow unlearning of what it meant to be anything at all. And in the last part of our walk, we saw the strangest thing of all, that the very word ending begins to come apart when you look at it too closely. That the mathematics of a cold, massless universe looks, from the inside, exactly like the mathematics of a Big Bang. That eternal inflation, if it is real, means our universe is one bubble among endless bubbles, and even a vacuum decay in ours is only the birth of a new bubble elsewhere. That every direction we look, endings dissolve into beginnings. That the cosmos, whatever it is not doing the thing we came here to describe. Because ending is a human word. We invented it. We needed it. We are creatures with lifespans. We know beginnings and endings from the inside. We know what it means to close a book and set it down. And we projected that shape, quietly, onto the cosmos. We assumed the universe must end because everything we know ends. We drew our tidy diagrams. We wrote our neat scenarios. We placed a final page at the far edge of the story. But the cosmos never learned that word. It never agreed to end. It only does what it does. And what it does in the deep future, whether it fades or rips or crunches or bounces or slurps or hands itself off into some new configuration we have not yet imagined, is not really ending in the human sense. It is transformation. It is dispersal. It is a slow, patient unmaking that never quite reaches a bottom. And that is the last, strangest lesson of the walk we took tonight. The universe will not end in the way a story ends. It will not end in the way a life ends. It will not close its own book. It will simply continue in some form past every horizon we can draw around it. There is no final page. There is only a fading of the ink and a widening of the paper until the words themselves become impossible to distinguish from the paper they were written on. Now, let that settle, and let me say something to you directly. Something I have wanted to say the whole time we have been walking. You are here, right now, in the pinprick of a moment we call the stelliferous era, in the brightest, briefest, most crowded chapter of the entire cosmic story. You are made of atoms that were forged in stars that died before your solar system formed. You are alive at a time when the sky is full of fires. You are alive at a time when a small species on a small blue world has, with astonishing patience, built instruments capable of measuring the far future of everything. You are alive during the 2 years in which our story of that future is being rewritten. Not in the next century, not in the next generation, right now in the season you are living in. And I know, because I know how the human mind works with numbers like these, that some part of you might be reaching for despair. Some part of you might be thinking, if it all fades, if it all forgets itself, if the last black hole flashes into nothing a Google years from now, what is the point of any of it? What is the point of anything I am doing tomorrow morning? I want to answer that gently before we say good night. The point is not that the ending doesn't come. The point is that the ending doesn't undo the happening. Every moment that has ever existed in this universe, every star that has ever burned, every planet that has ever spun, every conversation you have ever had with someone you loved has already happened. It is written into the shape of what has been. Nothing in the deep future can reach back and unwrite it. The cold quiet of the dark era does not travel backward in time and erase your morning coffee. It does not travel backward and erase the sound of your grandmother's voice. It does not travel backward and erase whatever it is you are going to do tomorrow that matters to you. The cosmos, in its long fading, does not cancel what has been. It only stops adding to it. And you are, right now, one of the things being added. Every thought you are having, every breath you are taking, every small kindness you are moving toward or moving away from, all of it is happening right now, inside the brightest window in the entire cosmic story. You are not late. You are not early. You are, in a very real sense, exactly where the universe is currently making things, where it is currently thinking, where it is currently loving, where it is currently trying to understand itself. You are a way that the cosmos, at this specific moment in its long life, gets to be aware. That is not a small thing. That is, in a way, the only thing. So if you have made it all the way to this point in the video, through 2 hours of endings and eras and equations and quiet expansions of the mind, I want to say thank you, genuinely. This channel exists because people like you sit through the long walks, because you let the ideas take their time, because you are willing to spend an evening or a night thinking about something bigger than yourself. If you found this journey valuable, a soft like or subscribe helps more people find their way here and helps us keep making these long, slow videos. It's a small thing on your end, and it matters more than you know on ours. And now, one last question. And I want you to sit with it honestly before you fall asleep. Tonight, having heard everything we have said, the 5 endings, the long eras, the way the very idea of ending dissolves under a close enough look, does knowing that the universe will one day forget itself change how you will live tomorrow? Or does it, in some strange, quiet way, make tomorrow feel a little more precious, a little more yours, a little more worth doing well? I would love to read your answer in the morning. Take your time with it. And now, take a slow, gentle breath. The stars above you tonight will outlast you, as they have outlasted every human being who has ever looked up at them. And then, in their own time, in eras so long they cannot be drawn on any diagram, they too will fade. And that is not sadness. That is the shape of everything that has ever been real, everything that ever loved, everything that ever burned, everything that ever mattered, has done so inside a cosmos that was always going to disperse. And it mattered anyway. It always mattered anyway. You are one of the ways it currently matters. Sleep well tonight. Sleep gently wherever you are. The universe is very old and very patient, and it has been holding you the whole time we have been talking. Sleep well under the stars. Good night.